Hello everyone, and welcome to our webinar today, which is an introduction to SCIA Engineer, Advanced Structural Analysis Made Simple. We're really happy all of you could join us. Here's a look at our agenda today. Of course, we'll get into each of these things in more detail, but just so you have an idea of what to expect in the next hour, here's a look at our agenda. We'll start with presenter introductions, then we'll get into an introduction of SCIA Engineer, the software itself. We'll look, of course, at a demonstration of the core features of SCIA Engineer. Then we'll take a look at some interesting case studies of some structures built here in the US using SCIA Engineer. And then we'll give you, of course, information on how to contact us if you have any questions or anything that you'd like to learn more about in the future. We'd be happy to hear from you. So let's go ahead and get started. Presenter introductions. Welcome again. Hi everyone, my name is Caitlin Metcalf. I am the Product Manager of Engineering Analysis at ALLPLAN here in our US office. I am a licensed California civil engineer, and I have 17 years of experience in the structural engineering industry, including extensive knowledge of analysis software, steel design, and of course I have several years of my own design experience to draw on as well. I'm currently working as a product manager, which means I help with the development of all of our engineering and analysis tools and features and functions within the ALLPLAN family of products, which gives me a great opportunity to try to help make things better, offer improvements in improved features and functions and tools to help the industry as a whole. It's a very exciting role. Today presenting with me is my colleague Keith Wan. He is the Customer Success Team Leader out of our SCIA UK office. He is responsible for training, technical content, and pre-sales, and is an excellent speaker, as you will soon see. He joined the SCIA UK team in 2019, but prior to that, he worked in consultancy for over 10 years in the United Kingdom, typically designing building and civil structures of all various sizes and uses. So let's go ahead and get started. Introduction to SCIA Engineer. Who are we? SCIA Engineer is an integrated multi-material structural analysis software and design tool that functions for all kinds of structures, simple to complex. Its wide range of functionality makes it the ideal partner for the design of office buildings, industrial plants, bridges, and more, all with the same easy-to-use modeling environment. SCIA Engineer was founded in 1974 and just recently merged with us in the ALLPLAN family just last year in 2024. So you may or may not know about the ALLPLAN family of products, but ALLPLAN is a global provider of BIM design software with lots of functionalities and a lot of support for various workflows and different design discipline needs. We focus on the delivery of building and infrastructure projects with an emphasis on equipping customers to increase efficiency in our design to build workflows. And our technical stack of products includes the original ALLPLAN software, which is more of an architectural drafting and concrete rebar detailing software. There's also the ALLPLAN Civil package, which is a bridge design product, and SCIA Engineer, Freelo, and DC, which are our various structural analysis products. SDS2, which is our steel detailing solution and connection design product. And all of these products work together on the BIM Plus platform, which is a cloud-based platform for model sharing, discipline, team member interaction and coordination, issue assignment, and live communication. All of them work together. So real simply, before we get into the demo and see the real depth of these benefits, let's just take a look at a simple list of the key benefits of SCIA Engineer. Of course, we have to start off with analysis and design. SCIA Engineer includes fast, comprehensive analysis and design of any structure from simple to complex. So it's really up to you whether you want to model something small to something very complex. We cover all sorts of analyses, all material types for all types of structures. It is a customizable program, so the customizable settings, parametrics, and toolbars allow you to customize the program design tools and interface and usage to fit your needs. Cutting-edge technologies are available to help you find efficiencies in every project. And of course, there's clear reporting on everything as well. Clear reporting output to make the review and revisions process simple, clean, and easy to follow. And this leads to a trusted design. Trusted, safe, and economical designs are simple output of SCIA Engineer based on the clear reporting and easy to follow revision process. So a little bit more about that design to build portfolio under the ALLPLAN technical stack. We'll get into it a little bit later on, and certainly we'll have some additional webinars as we move into the future. Specifically, SCIA Engineer and SDS2 work very nicely together through the design to build phases of conceptual design to fabrication and construction, including conceptual design, structural analysis and design, detailing, fabrication, and construction. These two products specifically work seamlessly together for your steel design product and other materials as well, but SDS2 is very focused on steel. So this works specifically very well for any sort of steel engineering design solution. SCIA's strength, of course, is the multi-material, multi-project, generic, complex analysis strength. You can really design anything that you want using that as your engineering tool. And SDS2's design strength is creating buildable, constructible steel structures with pre-checked structural connections designed as you model. So you get those connection design checks right up front prior to even sending it out for your official engineering analysis. These two products work perfectly together, and of course they both sit on the BIM Plus platform, so they make it very easy to work together as a team, coordinating not only with your engineers, detailers, and fabricators, but of course all the other members on your team as well. Transparency is the word. As you work between SCIA and SDS2 on the ALLPLAN platform, everything that you need is included in one workflow. All the tools you needed are shared and transparent to all the other members of the design team to have full informational access to everything, bringing trust and understanding and quick, efficient solutions to everybody on the design team. But again, as I mentioned, that's something we're going to dive into more specifically later. Let's take a step back now and take a look at the core features of SCIA Engineer. What can we as engineers use SCIA Engineer as today to model structures, the various structures and projects that we have coming up in our day-to-day portfolio? So for this, I'll hand this over to my colleague Keith, where he will give you a nice demonstration of SCIA Engineer.
Hello everybody. My name is Keith, and today I will be showing you a selection of steel analysis and design tools available to you in SCIA Engineer. All of them have been developed to offer you accuracy, transparency, and improved productivity. Hopefully by the end, you will like them just as much as we do. Let's use a relatively simple steel frame building to demonstrate some of the core features of SCIA Engineer. The model has some arbitrary loads applied for dead, live, roof, and snow loads. For this model, wind loads have been defined manually. Additionally, there are two seismic load cases which are based on a response spectrum. The self-weight load case is automatically calculated and defined in SCIA Engineer. All other load cases were manually created. The live load cases are assigned to appropriate load groups. For example, this load group for live loads will be considered for live load reduction as per the code. The roof live load is set up in a similar manner. The wind load cases are in one load group where the relationship is set to exclusive, preventing the wind load cases from appearing in the same combination when SCIA will automatically generate the load combinations later on. Now, let's change the graphic view to something more analytical. This structure features a couple of bracing types, but I want to highlight the 36 cross braces. All of them are defined as axial force only and have been assigned tension-only nonlinear behavior. Let's look at the automatic load combinations. These are all envelopes, meaning they can contain several load combinations and will give you the enveloped results. Strictly speaking, they are all linear analysis results. In this model, we have automatic envelope combinations for seismic, the pre-composite or construction stage, and the composite or final stage. You can see that both LRFD and ASD combinations are generated. These codified envelopes not only generate load combinations, but they will also select load factors based on the load case properties. If you expand the LRFD combination for the composite stage, i.e. the final stage, we find that it will generate 55 load combinations, each with corresponding load factors. As mentioned before, these 55 load combinations are effectively contained within a single envelope combination. Due to the tension-only cross-bracing, we will require a nonlinear analysis, so some nonlinear combinations have been defined. They are direct copies of the previously exploded combinations. We can use a result class to envelope these nonlinear combinations, allowing us to manage their results effectively. There are other result classes which were generated automatically. For example, there is a class that contains all LRFD combinations, another containing all ASD combinations, and another one that contains both ASD and LRFD combinations together. There's also a special result class for composite design that is specifically used in the composite beam check. Next, let's review the deformations. Starting with the dead load deformation in a wireframe view. We can switch to a rendered view for a clearer perspective. Currently, we're displaying the results for one load case, so we can switch to one of the wind load cases. These types of results are great for gaining a basic understanding of the structural behavior, and also to give you confidence in the model. Now, let's move on to the reactions that the column supports. For this, we'll use the final stage LRFD combination. Remember that these vertical reactions represent an envelope of multiple load combinations. So these reactions won't necessarily be due to the same combination of loading. In the report preview, we can observe the reaction values for each support, where the bold cells indicate the extreme values. By activating the Action on Support toggle button, we can tabulate this table for every node per load case. This is very helpful when you need to give loads to the foundation engineer. If you need to relate this table to the model, then displaying the relevant node labels is straightforward. We simply highlight the nodes and toggle on the node labels. Let's quickly focus on one of the flaws. Flexible result filters allow you to quickly identify members that need your attention. For example, starting with the LRFD envelope for the pre-composite stage, you can quickly find the worst bending moment for all floor beams. Likewise, you can do the same for the shear force. Moving to the composite stage, we can quickly retrieve the worst shear force and moment values. And if you want to delve deeper into a specific beam, you can display multiple forces simultaneously. For example, the shear force and bending moment. Now, let's take a quick overview of the composite beam design. The composite beam check is an all-in-one tool that verifies both serviceability and strength in the construction and final stage. After running the design, we can quickly see that all beams satisfy the code, because everything is green. You can view a detailed design report, which provides comprehensive background calculations, including the stud layout. Both strength and serviceability checks are conducted. You can also obtain a more condensed view using the summary output level. This level of information is perfect for reporting and getting quick insights. Let's focus on the roof structure now. Here, we're dealing with standard steel, so not composite beams. Let's immediately go to the steel serviceability check. We'll evaluate the relative deflections of each member using an ASD combination. The overall unity check is great for getting a quick understanding of how each beam is performing in terms of deformation. For example, you can clearly see that all members are green. Therefore, their deflection is less than the required deflection limits. We requested the worst performing beam, i.e., the beam closest to its deflection limits. And on screen, its unity value is the only one displayed. So it's very easy to visually pinpoint areas of interest. You might be interested in the beam with the greatest relative deformation, regardless of its deflection limits. In that case, instead of the unity value, you can examine the actual calculated deformation. For example, the vertical deformation due to dead and live load. Now, let's look at the same deformation value, but for the member with the highest utilization. You have all the same result values available for both the vertical and horizontal direction, including the calculated limits. As you can see, we could have requested additional deformation results, such as those resulting from live loads, along with their corresponding limits. If you generate a report preview, you'll see a well-organized tabular output that summarizes the deformation results due to the total load and variable loads. Had the model been set up to design camber and the program detected the requirement, you would also see the designed camber values here too. Now, let's dive into the steel strength check. This time, we'll use the result class that contains all ULS combinations or strength combinations, specifically the LRFD combinations including seismic. Using a simple and intuitive color system, we can immediately see that several members are failing. The red areas indicate some failure to meet the design code, whereas the green or grey areas denote varying levels of adequacy. Currently, only the highest utilization value is displayed. you can easily adjust the result properties to examine other member values. Let's focus on the worst performing beam. Now we'll explore the Auto Design tool. This will search the profile catalog to optimize the cross-section. Any member assigned to the same cross-section will also be affected. So cross-sections actually behave like a sort of design group in SCIA Engineer. The target unity value is currently set to 1. And we'll use this to search for the optimal cross-section within the same catalog. You can prioritize the search criteria based on the cross-section height, mass, or even inertia. After optimizing the cross-section, we can recheck the member. Now we can see that this member now successfully passes the strength check. Returning to the other members, and again focusing on the worst one, we can request the brief report preview. The brief report gives you a quick insight into the governing failure modes, where the highest unity check value is the most critical. For example, the report shows the combined forces check is the most critical. At the same time, you can see that the bending check is failing as well. So it's more than likely that resolving the bending failure will help the combined check. To investigate further, you can switch the output level to detailed. Now we have access to much more of the background information, presented in a tabular format. We can expand this by including formulas and tables. This allows you to really scrutinize the design calculations. These formulas also clearly reference the design code. If we scroll down to the bending check, we can pinpoint the cause of the failure. The nominal flexural strength appears low, primarily due to lateral torsional buckling. We could resize the member as before using the Auto Design tool, but we can also introduce additional LTB restraints to all members to improve the flexural strength. This is a relatively straightforward thing to do in SCIA. For example, you can define some discrete restraints along the top flange, representing purlins that you haven't directly modeled. With the LTB restraints in place, we can rerun the check considering the additional restraints. And now you can see the members satisfy all design checks. Finally, let's check the rest of the steel members. Immediately, you can see that the cross bracing fails. This is because we're using a result class that contains linear results, leading to the bracing members failing in compression, which is not their intended function. But this is easily corrected. You just need to switch to the result class that contains all the nonlinear combinations. The nonlinear analysis takes into account the tension-only behavior of the cross bracing. With this adjustment, the cross bracing now functions correctly, operating in only tension. However, notice that some other members are now failing. This is because the whole structure is affected to some degree. Once again, we can utilize the Auto Design tool to quickly resize these failing members. You may be curious about how SCIA Engineer incorporates notional loads. To start, let's clarify what notional loading represents. Essentially, it reflects the forces generated by deviations in construction, i.e. the structure being out of plumb or the beams not being perfectly straight. It is possible to manually calculate notional loads and then add them to your SCIA model. However, there is a better way. In SCIA, you can apply a global imperfection to your model, which represents its outer plumbness. This way, the analysis will automatically account for the additional forces. This approach is more precise and allows you to better utilize the power of your computer. Setting up these global imperfections is simple. We start by enabling the necessary functionality in the project settings. Crucially, we need to activate initial imperfections. This is what will allow you to apply global imperfections for outer plumbness and local imperfections for outer straightness. In addition, you do have the option to activate geometrical nonlinearity, which allows you to calculate a second-order analysis. After making those changes, a new menu item labeled Global Imperfections appears. Normally, you would need to create 4 global imperfections, one for the positive x direction, one for the positive y direction, and likewise another 2 for the negative x and y directions. For this demonstration, we'll define only 2 directions. Starting with the positive x direction, we will define a simple inclination, for example, h/500 in the x direction. Then, we can repeat those steps for the positive y direction. In a comprehensive project, we would also create 2 additional imperfections for the negative x and y directions, but for the sake of demonstrating the concept, we will focus on just 2. With the global imperfections established, we can now link them to the nonlinear combinations. For example, we can link all of the nonlinear combinations to the global imperfection for the positive x direction. Now, we need to copy all of the combinations and reassign them to the global imperfection for the positive y direction. And in theory, you would need to do this another 2 times for the negative directions. And this is really the only drawback of this approach, the fact that you multiply the number of nonlinear combinations by the number of global imperfections. This means there will be a greater demand on your computer. However, SCIA's FE solver combined with today's technology means the analysis calculation is the fastest it's ever been. After the analysis is complete, you can view the applied imperfections via the 3D deformations. When linked to a nonlinear combination, as we did before, this imperfect shape becomes the initial shape that will be used for the analysis. Therefore, notional loads are not actually required because their effects are already accounted for at the analysis level. Returning to the nonlinear result class, we can see the new combinations have been added automatically. The only thing you need to do now is make sure you use a nonlinear result class that contains all of the nonlinear combinations. So for example, we can rerun the steel strength check. Using global imperfections with nonlinear analysis is the first step towards using SCIA for the direct analysis method. There are a couple of more steps that you would need to do, but we don't have too much time, so let's not go into that much detail. But perhaps that's a topic for another time. When you're happy with the design, you might want to get an understanding of how much steel is in your model. In that case, you can use the bill of material. Here, you can see the total length and mass of steel for each cross-section type. Do you find that it takes a lot of time to collect data from the analysis and the design? Even more so if you want to organize it into a presentable format for someone to review. For this tedious but important task, the engineering report in SCIA can help you save a lot of time. We can begin assembling a collection of images and results to incorporate into the engineering report even before we start. For example, we can save a live image and send it to the inbox. Likewise, we can save results to the inbox as well. So, as another example, we can save the results from the bill of material to the inbox. These inbox items can be inserted into the engineering report at any time. Both the image and the results are live, meaning they can be updated with minimal effort in case you make any changes to the model. When we first open a report, it's blank. The navigator on the left side of your screen will show all the items that will be included. We can add items to the navigator from the available items tree, and this is very simple and intuitive to do. For example, we can add a table of contents, header and footer, and chapter markers. Every item has a set of properties which you can change. For example, you can change the chapter caption. We can now add the image and the result we saved earlier from the inbox. In addition, we can directly insert items from the available items tree, such as the cross sections from the model. We have the flexibility to adjust section numbering by indenting or outdenting selected items. Any changes will be reflected in the table of contents. Now, let's create a new chapter for loads. This time, we can utilize the search function to quickly filter through the available items. So it is very easy to find what you're looking for, even if you don't know the exact name. Since all this data is live, we can leverage some pretty impressive features. For example, we can prepare an image that illustrates the loading conditions for one load case. And then add this as a live image to the report. Now, let's indent the image and the surface loads under the load case item. After regenerating, you can see that an image and a set of surface loads is automatically created for each load case. And this is all being generated from one image. If you want to make any adjustments to the image, we can modify the view parameters accordingly. For instance, we can include the loading labels. And again, after regenerating, you can see the image displays the magnitude of each load. Finally, we'll create another chapter for the design of a frame. This could equally be for the entire structure, but let's just focus on one frame. We can set up SCIA Engineer for the desired result image and properties. When everything is set, we can send the live image and the result table directly to the report. The exact same approach applies to the design check. For example, you can send the result image and table for the steel strength check to the report. Returning to the report, we can see that all of the items have been successfully added, and the detail is at the same level as we saw in SCIA Engineer earlier. To make you even more productive, you can save the navigator item list as a template, meaning you don't have to start every engineering report from scratch. So for your next project, you could start the engineering report from a template. You can even send that template file to your colleagues to save them time. You can directly import DXF and DWG files into SCIA, and you can choose to import the drawing as simple lines or polygons. Alternatively, you can convert them into 1D and 2D FE members directly. With SCIA and ALLPLAN, you have various options to exchange BIM model data. You could use BIM Plus, which is an open BIM model data platform, purposely designed for project collaboration across all disciplines. More directly in SCIA, you could import an IFC file. And of course, there are links to and from Revit and Tekla structures. Finally, you can exchange data via SAF, which is an open exchange format for structural analysis and design programs. In that case, we have great compatibility with STS2, Reza, ALLPLAN, and Graphisoft, just to name a few. To summarize what you've just seen, you can do a lot with SCIA. You have advanced analysis capabilities, but at the same time, they're relatively easy to use, especially for 3D models. You can then use the analysis results with the program's steel design checks, all according to AISC 360. And then you can put all of that into a clear and detailed report, which can automatically update itself. Finally, I hope that you got an idea of our commitment to openness and collaboration by the many options you have for data exchange. Sadly, we need to move on now, but I hope that you saw that SCIA is an integrated analysis and design program. It's one program for modeling, analysis, design, and reporting, all streamlined into one workflow.
Thank you, Keith. Great presentation. I hope that gave everybody a lot of ideas and started the wheels turning on how you might be able to utilize SCIA Engineer in your own day-to-day workflows. To give you further inspiration, I'll take a look at a few case studies that I've gathered from some engineers here in the U.S. who have used SCIA Engineer for various project building, and we'll take a look at some of those, some of the issues that they had on various large-style complex projects and how they were able to overcome those issues utilizing the easy-to-use modeling tools of SCIA Engineer. Our first case study is an office and warehouse building out of Logan, Utah. As you can see, it is a paneled system, so the walls, the floor, and the roof system are all panelized composite concrete system. And those were modeled, of course, as you can see here, in SCIA Engineer using the three-dimensional finite element method. The complex layout of all of those panels was easily modeled using the finite element panels within SCIA Engineer, and then design loading was applied to the structure manually and utilizing the integrated wind force generator within SCIA Engineer. The ACI design module then was able to identify locations where additional reinforcement was necessary based on the design checks. Our next case study is a storage rack system located in Santa Monica, California. This was shared with us by Fraser Industrial Company. And as you can see, the 3D analysis model was created using SCIA Engineer. They actually were able to create it based on combining block templates that they had pre-built for other similar projects. So they were able to use those templates, bring them together to combine and create a cohesive structure based on other racking designs that they had used on other projects. The seismic forces and product loads were then applied by parameter variables and then coded into the templates for easy application and variation. Load panels were used to represent the platforms and distribute live load into the framing structure. The stiffness of the beam to column connections was modeled directly using spring stiffness, which was determined by testing outside of the program. The load panel distribution of product and seismic load ensures that the member forces, deflections, and support reactions are consistent throughout the multi-level structure. Then for analysis, the engineering report was kept up to date using live pictures, tables, and design forms to present the model inputs and results of the analysis, even as it changed throughout the many revisions of the design process. Another cool case study is this mezzanine bridge suspension that's part of an indoor space in Portland, Oregon. This was an indoor space, an indoor suspension bridge that was moved from another location in the city into this indoor space. And in order to stay true to the structure and fit within the new space, cables could not be placed solely as architectural elements, but also needed to actually support the curved mezzanine edge. So determining the structural loading of the cables and the subsequent optimal cable locations was very challenging, as the cables follow a curved form both at the bottom points and at the top points of their connection. And then, of course, because that meant that the tributary area of the loading to each cable varied. To determine these cable locations, the architect first passed a three-dimensional model with their idea to the engineer. This was then imported into SCIA Engineer, and all the appropriate loads were then applied. The deflected form of the model was determined, and the nodes were moved around to their proper locations based on that loading to refine the design. This revised model was then passed back to the architect for formal acceptance. When a final shape was agreed upon, the cables and supporting steel structure were designed for their final loading. Very cool. My last case study is a canopy roof, also from the KPFF engineers. This is located in Eugene, Oregon, up at the University of Oregon, and it is a softball canopy roof over the Jane Sanders Stadium. This structure is in a high seismic zone, and a number of lateral analyses were needed to be carried out in order to determine whether the large structure would be stable in an earthquake event. Wind loads were also carefully considered, as the structure is shaped like an airplane or duck's wings, leading to concerns that it might want to lift off of its supports under lateral loads. Construction of the canopy roof was also a major consideration. To meet tight scheduling requirements, the canopy would be fabricated in the field and lifted into place. The engineers and contractors considered lifting in two pieces and designed the roof initially for this, but it was finally determined that lifting it in one piece, including the applied roof decking, was more efficient. Very cool, and you can see it's happily in use today. That's it for our case studies, just a few to inspire you all there. Hopefully you all have thought of some ideas of how you might apply some of these ideas and tools within your own workflows. If you're interested in learning more, we encourage you to contact us at any time. As I've mentioned now, we are planning on having future webinars and more specific detailed webinars on how SCIA Engineer will integrate with our other products within the ALLPLAN suite of structural analysis products. Please feel free, though, at any time to contact us at our email address where you can reach out for more information, pricing, etc. You can also access tutorials and trainings on the SCIA website, which is just scia.net. And please keep your eyes and ears open. LinkedIn, our email contacts, all of our communication efforts will be announcing future webinars as they come. So keep your eyes open and we'll be sure to reach out and share more with you. If you have any other questions, please feel free to reach out at any time. We're happy to answer anything at any time. I hope you have a great rest of your day, and I thank you very much for joining us and giving us your attention. Take care.